This is a video from section 3.6, and we're going to look at derivatives of inverse trigonometric functions. But before we do, we need to review a few concepts. Number one, y equals arc sine of x means x equals sine of y, where y is greater than or equal to negative pi over 2 and less than or equal to pi over 2. Number two, y equals arc cosine of x means x equals cosine y, where y is greater than or equal to 0 and less than or equal to pi. Number three, y equals arc tangent of x means x equals tangent y, where y is strictly greater than negative pi over 2 and less than pi over 2. Okay, so that's the first piece. Now, in the second piece, we have the following. Sine squared x plus cosine squared x is equal to 1. But we need to be able to view this in a few different ways. So in other words, if I see something like cosine squared x, we need to be able to view this as 1 minus sine squared x. And then they can switch places, right? So in other words, if I have sine squared x, we can write this as 1 minus cosine squared x, like so. Okay, now, let's start with sine squared x plus cosine squared x is equal to 1. I can divide both sides by cosine squared x. So I'm going to divide sine squared x by cosine squared x, divide cosine squared x by cosine squared x, and then divide 1 by cosine squared x. And so on number 5, this says tangent squared x plus 1 is the same thing as secant squared x. Okay? Now, here's where the fun begins. So, for example, I'm going to let y equal the arc sine of x. And I want to find dy dx. Okay? So we're going to start with y equals arc sine of x. And let's solve for x. Now, when I do that, I get x equals sine of y. But remember, y is less than or equal to pi over 2 and greater than or equal to negative pi over 2. Now we want to differentiate, and I'll write it out, differentiate both sides with respect to x. Now, when I do that, I get 1 equals cosine y times dy dx. So that says dy dx is 1 over cosine y. But remember what I said, okay? Now let's go over something here. Remember that cosine squared y is the same thing as 1 minus sine squared y. And what I want to do is I want to take the square root of both sides. So far, so good. And this is an important note. Remember, y is less than or equal to pi over 2 and greater than or equal to negative pi over 2. And so therefore, cosine of y must be positive. Or, well, a little better than that. We can say cosine of y is greater than or equal to 0. I don't need 4 dots, I just need 3. Okay? And so therefore, cosine of y is equal to the square root of 1 minus sine squared y. So I didn't have to put absolute value bars around cosine of y. And so therefore, coming down here, we can say dy dx is 1 over the square root of 1 minus sine squared y. But x equals sine of y. And so dy dx is equal to 1 over the square root of 1 minus x squared. And so therefore, the derivative of arc sine x with respect to x is 1 over the square root of 1 minus x squared. So let's take a look at this example. Suppose I let y equal the inverse tangent or arc tangent of x. So solving for x, we get x equals tangent y. And remember, y is less than pi over 2, and it's greater than negative pi over 2, right? So differentiating, we get 1 equals secant squared y times dy dx. It's just chain rule. It's really slick. So dy dx is 1 over secant squared y. But this is where we got to get comfortable. Remember, secant squared y is 1 plus tangent squared y. And so dy dx is 1 over 1 plus tangent squared y. But x equals tangent y. And so dy dx is 1 over 1 plus, substituting that in, x squared. And then just to wrap this one up, we can say, therefore, the derivative of arctangent x with respect to x is 1 over 1 plus x squared. I want people to know this one. This one comes up all the time. This derivative comes up. The derivative of arc sine x comes up. It comes up a lot. A lot. And I want to do one more. So we'll call this, we'll go over the next example and find the derivative of arc cosine x. And that's a pretty good exercise. So if we solve for x, x equals cosine y. And remember, we need to be mindful of our restriction. Y is greater than or equal to 0 and less than or equal to pi. We can differentiate both sides with respect to x. So 1 is negative sine of y times dy dx. So dy dx is negative 1 divided by sine of y. But just like in the very first example, when you look at sine squared y, we have to be able to view that as 1 minus cosine squared y. We have to. Now, remember, sine of y is greater than or equal to 0 as long as y is between 0 and pi. Okay? That's a fact. That's important, right? So look. So we have sine squared y is 1 minus cosine squared y. We're going to take the square root of both sides. So we can now freely say sine of y is the square root of 1 minus cosine squared y. Now, we just established that dy dx is negative 1 over sine of y, right? But this is negative 1 over the square root of 1 minus cosine squared y. But didn't we just get through saying x equals cosine y? And so dy dx is negative 1 divided by the square root of 1 minus x squared. Okay. And we're almost done, because we can now conclude that the derivative of arc cosine x with respect to x is negative 1 divided by the square root of 1 minus x squared. And they could pretty much be derived in this fashion. It's really pretty good. Let's take a few derivatives. And let's start off with the first example. Suppose I said y equals the inverse sine of 5x. And it's pretty cool to use Leibniz notation. And so I'm going to let u equal the inside function of 5x. So y is arc sine of u. Du dx is equal to 5. Dy du is 1 divided by the square root of 1 minus u squared. Okay. Dy dx is dy du times du dx, which is 1 over the square root of 1 minus u squared times 5. I hope that's okay. Now remember, u equals 5x, right? So if I take u and square it, I get 25x squared. 5 squared is 25, and then I just square the x. So dy dx is 5 divided by the square root of 1 minus 25x squared. And that's how we do the first example. Let's take a look at the second example. Suppose I had y equals arctangent of x squared. U is x squared. Du dx is equal to 2x, right? Y expressed in terms of u is arctangent of u. It's good to be able to establish what the inside function is, right? This is really, really good practice for when we get to u substitution for integration. dy du is going to be 1 over 1 plus u squared. Now, one thing to keep note of, u is x squared, right? So if I square both sides, u squared is x raised to the 4th power. So dy dx is dy du, which is 1 over 1 plus u squared, times du dx, which is 2x. And so, therefore, dy dx is 2x divided by 1 plus x raised to the 4th power. And that's how we take the derivative of the second example. And we'll do one more for this video here. Let's take a look at this one. So if I have y equals arctangent x raised to the 2nd power, I'm going to let u equal the arctangent of x. So y is u squared. Du dx is 1 over 1 plus x squared. So you notice it's always a game of what's inside, what's outside. Dy du is 2u. Let's write that again. And so dy dx is dy du, which is 2u, times du dx, which is 1 over 1 plus x squared. But u is arctangent of x. And then I just divide by 1 plus x squared. And so, therefore, dy dx is 2 arctangent of x over 1 plus x squared. And I think that's a good stopping point for this video. This is a video on section 3.6, and we did 3 examples of finding inverse trigonometric functions and then some review of concepts that will help us find those derivatives. Okay, thank you.